Have you ever stopped to think about how your computer can download a huge file, play your favorite music, and let you type in a document all at the exact same time without completely grinding to a halt? Well, the magic behind all of that is a concept called multithreading. So let's break down how it all works. To really get it, I want you to imagine a super busy restaurant. Tables are packed, people are ordering, food's flying out of the kitchen, bills need paying, the works. Now, what if there was only one single waiter trying to do everything? It would be total chaos, wouldn't it? Customers would wait forever, orders would get mixed up, the whole place would just fall apart. Well, believe it or not, that exact problem, managing total chaos and keeping everything running smoothly, is something your computer's processor, its CPU, solves thousands of times every single second. And the way it does it, that's the secret sauce behind almost all modern, responsive software. So what's the obvious fix for our restaurant with the one completely overwhelmed waiter? You hire more waiters, of course. And in the world of computing, that's precisely what multi-threading is. It's like bringing in a whole team to handle the dinner rush, turning that chaos into a beautifully smooth operation. Okay, so let's get just a little technical for a second. The formal definition of multi-threading is that it's a feature that lets a program break its work down into smaller pieces, little subtasks that can all run at the same time. The goal here is really simple. You want to squeeze every last drop of performance out of that CPU. You never want it just sitting around doing nothing when there's work to be done. And this is a perfect way to visualize it. The entire program you're running, say your web browser, is the process. That's our restaurant. And the individual tasks, like loading an image or playing a video, are the threads. Those are our waiters. They all work for the same restaurant, but each one is handling a different job, all at once. And that brings us to a really crucial difference in how things get done. See, before multi-threading was the norm, computers worked just like our single, stressed-out waiter. Now, they work like a perfectly coordinated team. Let's take a look at what that actually means. This diagram just nails the difference. Over on the left, you've got sequential execution. It's a single file line. Task A has to be completely finished before task B can even think about starting. But look at the right. That's parallel execution. You've got multiple threads running at the same time. You can just see how this massively slashes the total time it takes to get everything done. But here's the thing. A thread, just like our waiter, isn't always sprinting at full speed. It has a whole life cycle. A waiter might be waiting for the kitchen to plate a dish, or maybe waiting for a customer to finally decide what they want for dessert. A thread is no different. It goes through several very distinct states during its journey. So let's walk through these. A thread starts as new the moment it's created. That's our waiter clocking in for their shift. Then it becomes runnable, meaning it's ready to go but just waiting for the CPU to give it a task. Running is pretty self-explanatory. It's actively doing its job, serving a table. Blocked means it's stuck, waiting for something, like that dish from the kitchen. And finally, terminated means its job is done, shifts over. And you can see that whole journey mapped out right here. A thread is born, it becomes runnable, then the CPU picks it up and it starts running. But notice how it can get bumped into a waiting state. Maybe it's told to sleep for a bit, or it's waiting on another thread, before it can become runnable again. And then, once its work is finally complete, it's terminated. Okay, so having a whole team of waiters is great for getting things done fast. But what happens when two of your waiters try to update the same table's bill at the exact same time? One adds a drink, the other adds a dessert. Whose version is right? This is where we hit the single biggest challenge in all of multithreading. And this right here is the million-dollar question for any programmer who works with threads. When you've got multiple threads all trying to read and write to the exact same piece of information, like, say, your bank account balance, things can get very, very messy very fast. The result is something called a race condition. It's basically a bug where the final outcome depends entirely on the unpredictable, random order the threads happen to run in. This can lead to totally corrupted data, and worst of all, bugs that are an absolute nightmare to track down, because they might only pop up one time in 1,000. So how do we stop our waiters from colliding and making a mess of the bills? Simple. We bring in a manager. The manager's whole job is to make sure that the supercritical tasks, like handling money, are done one at a time in an orderly way. And in programming, we call this synchronization. The main tool for this job is a special keyword called synchronized. When a developer uses this, they're basically putting up a big sign that says, hey, this part of the code is critical. Only one thread in here at a time, please. It's the manager telling one waiter, you finish with that bill completely before anyone else is allowed to even look at it. So here's how it works. Think of it like a single key to the manager's office where the cash register is. The first thread that gets there acquires a lock. It gets the key. And as long as it has that key, any other thread that comes along has to wait outside in a line. Once the first thread is finished, it releases the lock, basically handing the key to the next thread in line. Now, this is incredibly safe, but you can probably see the trade-off. Making other threads wait can slow things down. So developers have to be really smart about using it only where it's absolutely necessary. And just to give you a quick peek behind the curtain, these are some of the actual tools developers use to manage all these threads. They can start them up, define what they actually do in the run method, tell them to sleep for a little while, or even make one thread join or wait for another one to finish its job. It's a pretty powerful toolkit for choreographing this incredibly complex dance. So the next time you're scrolling through your social media feed while a video is loading in the background and music is playing, you can thank multithreading. It really is the invisible engine that makes all of our modern software feel so fast, so fluid, and so responsive. It's all about making sure no part of your computer's brain is ever just sitting around bored. And that leaves us with a pretty big question to think about. As our devices get more and more powerful, packing in more and more processor cores, this delicate dance of managing hundreds or even thousands of threads is only going to get more complex. So how are we going to manage that ever-growing team of digital waiters to get even better performance in the future? It's definitely something to think about.